point. But it still provides differentiation from the scalable microprocessor-based machines because it has much, much higher performing processors and a much higher bandwidth memory subsystem and a higher bandwidth interconnect and a more tightly integrated interconnect than you'll see in other systems that are being sold today.
Our goals for the SV2 software are, first of all, to provide a smooth transition for our existing customers, those customers being the parallel vector SV1 and T90 customers and the MPP customers of the T3E. The second goal is to provide the hardware architecture, deliver the hardware architecture to the software applications. This has always been an important goal at Cray. We provide unique hardware. We want to make sure that the customers can take advantage of that hardware by delivering it through compilers and operating systems and other system software that we develop.
With the SV2, we are using a distributed shared memory system architecture, which is similar from a system architecture point of view to scalable microprocessor-based machines. So the same sorts of optimizations that people are getting increasingly comfortable with doing will apply to the SV2. You'll do data decomposition and work decomposition and blocking for fitting workloads into cache, just like you do on microprocessor-based machines. So the SV2 will look a lot more similar to mainstream machines in terms of the types of optimization that the programmer has to think about. Then the compiler will take that code and compile it onto the SV2 and vectorize it, and this alleviates any thinking that the programmer has to do to customize the code for a vector machine.
I think a big advantage for customers moving to SV2 that have come from the T3 environment is that they can actually augment their traditional processing with vector processing. So, and this is done in a way that's transparent to the users. So the compiler will be delivering the vector underpinnings to, say, an MPI application, and the customer will be able to take advantage of the things that you get with vectorization, like high bandwidth to memory, automatically with this new architecture and the compiler support.
You need to have an operating system that treats the entire machine as a single system, which of course we do. This is another difference between a machine like the SV2 versus a cluster-based machine. In a cluster, you've got an operating system that is in charge of controlling a small number of processors, and then you take a whole bunch of these, cobble them together, and you have a whole bunch of separate operating systems that try to communicate with each other. Whereas in the SV2, there's one operating system spanning the entire machine. It can do process scheduling, it can do resource management, it can do fast communication amongst itself, manages the entire system as a single entity.
We're carrying forward some key technology that we developed for the T3E platform, and that is the global resource management technology. This is the technology that allowed T3E applications to be scheduled very efficiently, and there were really two benefits to customers. One is the repeatability of application performance through a gang scheduling techniques, and the second one is the ability to get high utilization out of a large multi-CPU system. Really, this is unprecedented in the industry. Cray is the only one that's really been able to do this with the T3E, and we've captured this technology. In fact, we're porting this technology over to SV2. So SV2 customers who are used to launching applications as they did on the T3E will find almost identical environment on SV2. One thing sort of stands out in this technology that we're investing quite a bit in for the future, and that's support of multi-streaming processors. The multi-streaming CPU concept on SV2 is unique. It allows execution of 4 parallel streams synchronized by some very sophisticated synchronization primitives, and all sharing a common cache architecture.
One of the things that occurs naturally when you go to a distributed shared memory system architecture is that you do data decomposition and blocking to fit in caches. Well, when you take a code that's been blocked to fit in caches, it tends to have a lot of short nested two-dimensional loops. And a short nested two-dimensional loop doesn't have long vector lengths. So a wide pipe machine is not going to run well on that sort of a code. What you can do instead with a multi-stream processor is apply each of the 2-pipe single-stream processors to a different iteration of the outer loop and give each one of them an entire copy of the inner loop. This allows you to run effectively because the 2-pipe processor can be effectively applied to a short loop, and you end up applying each one of your single-stream processors on a different inner loop, and they can be kept effective even though you have short nested loops. So it's this flexibility of being able to apply the 8-vector pipes at different levels that gives multi-stream processing a greater ability to run on a variety of codes and makes it fit particularly well into a distributed shared memory system. We have talked to people at various government labs that have told us that they're looking forward to the SV2 coming out, and they expect breakthroughs. They expect to be able to do things that they have heretofore not been able to do. So we expect this to be true both in the government arena and as well as various industrial arenas, that the most challenging problems that the scientists and engineers at the forefront, at the flame front, are wanting to do but can't, will be enabled.